Today we're going to go over the notes on work, energy, and power. Energy. Okay, let's start with work. Work is just equal to a force applied times the distance the object moves. Okay, so this means if I have an object and I apply a force, that object is now going to move along the floor some distance here. So work is just equal to the force times that distance. Now the big thing with work is those two things, the force and the distance, must be parallel to each other. So we put this little parallel symbol in there to remind us of that. Okay, so that means if I had an object and I applied a force like this, but the object moved that way for some reason, I don't see how that could really happen, the work in this case would be zero. The force and the distance are perpendicular to each other. Okay, a more actual thing that might happen is we're pushing a box along the floor. We're pushing down on the box because we are taller than the box. As we push down, this is my force, but my box moves this distance. We just talked about trig functions, so if we broke this force apart into the force that's applied in the x direction, that would now be my work. Force in the x direction times the distance. So that's the big thing about work. Okay, the force and the distance must be parallel. The units that we deal with this, if we're looking in the metric system, we have something that's called a joule, which is just a capital J. Okay, force, we measure that in foot pounds, really, if we look in English, and then distance is in feet usually. And so the units in the English system or our pounds of force that we're pushing with times the feet. Pounds times feet. And we just write that as foot pounds. Okay? So that is work. The next thing we want to look at is called energy. Next, let's look at energy. Energy is just the ability to do work. So energy and work are really the same thing. Okay, so when we talk about work, we're also talking about energy. Now there's two other types of energy that we talk about quite a bit, and those are called kinetic energy. This is just energy of motion. Okay, and we also talk about potential energy. This is energy of position. Let's get that way you can see it. So energy of motion, so kinetic energy K is equal to 1/2 mass times velocity squared. So there's that motion. Velocity is speed or movement. So anytime something is moving, we're going to have kinetic energy. Okay, potential energy, the main one we talk about is gravitational potential energy. So potential energy, a lot of times they use a U. Sometimes you'll see it as a PE for potential energy. Okay, so this is equal to mgh. So it's energy of position. The position that we're talking about is height. The other two things are mass and the acceleration of gravity, because it's gravitational potential energy. Sometimes we put a little g there to remind us of that. That's gravity pulling down on me. So if I have height, so if I'm standing on the table or standing on the roof, I have height above the ground. So I have the potential to fall off that roof. Right? So I'm standing up here on the roof. I have the potential to fall, and so I have energy because of this position. As I fall, so if I tripped and fell off the roof and now I'm falling through the air, right? And I'm falling through the air here. As I'm falling, I am moving, and now I have kinetic energy. The higher I am, the more potential energy I have. So as I fall, I am losing potential. Okay, so my potential energy is going down as I fall. My kinetic energy is going up because I'm getting faster and faster as I fall. And so this leads us into our next concept, which is called conservation of energy. Conservation of energy. And this just says that energy is not created or destroyed. It only changes form. So just like the example that I was showing, sorry, get better at this as we go. The example that I was showing here, we have potential. How did we get that potential? Maybe there's stairs that we were walking up. Wonderful stairs there. Okay, not a good engineer that built those stairs. But as we walk up these stairs, we did work, right? We had a force that we lifted with the muscles of our legs. So every time we went up a stair, we used force to get us to the top, and we went through some distance. That force times distance, called work, going up the stairs, as we do that with that force times distance, that's now equal to the potential energy that I have for being up on the roof. That potential energy as we fall turns into that kinetic energy, and all those are the same. Okay, so the work that we started with, we gain and we get that as our our potential energy of our height, our position, which falls down when we fall to the bottom, and all that work that we originally created ended up as potential or kinetic. Okay, now as we hit the ground and we go splat here on the bottom, okay, right, we're not happy if we hit the bottom down here. What happened to all that energy there? You're like, energy disappeared. It did not. We heard the splat, so there's sound energy. When we hit, there was some energy that went off as little shock waves into the earth. There was heat created. If you slap your hands a long time or slap the table, you'll build up heat. So that energy went somewhere else. Okay? So nothing is created, nothing is destroyed. It merely changes form. Sorry, I had to pause for a minute. So basically what we're saying here is that work, energy is all the same, and so it's all conserved. Okay, so the net work, the work done on an object, is equal all to its change in energy, whether it's changing from potential to kinetic to sound to heat, whatever it is, energy just changes. We only look at mechanical energy basically in this class, which is potential and kinetic, and then we might look at gravitational mostly. There's also elastic energy. We don't talk much about any of that. But when we do work on a system, right, just like our person walking up the stairs, we're doing work on the system. The system is the person. He's doing work. Okay, energy is gained. We're getting energy into that system. Now we're taking it from somewhere. Remember, it's our muscles, so we're taking energy. Came from the sun originally that grew the plant that we ate, that went into our muscles, and turns into the sugars and all the stuff that you learn in biology to get that energy to move up here. Okay, now as we go through, if we do work on the system, we're providing energy. So we're providing energy to the system, right? As we fall down and we hit the ground, the energy is going out. There's heat through the air as we have friction. When we hit the ground, we have heat. We have the sound. We have the little shock waves that go through the ground, right? When we came down here. So doing work on a system gives it energy. The system doing work provides energy. So you have to define your system. And our system in this case is the person. Okay, so that's conservation of energy. And then the last thing we're going to talk about was work, energy, and power. So if we talk about power, power is the rate that work is done. So our equation for this is power equals work divided by time. And it's really the change in time, how much time took place or happened while that work was being done. Okay? If we do this, the unit for power, work, remember it was in joules typically, and time is in seconds. We now call this a watt, which is the same as a capital W. So you got to be careful because work is a W, watt is a W. We start to get these units and these variables that look the same. Okay? But now remember, work is force times distance. We can also write this force times distance over time. Okay, remember the work that we put in was equal to the potential energy that we now have, so we could replace this with mgh over time. Okay, so you can rearrange these things a lot, and this is where sometimes this class gets a little more difficult, in that we can substitute a lot of things, and you have to look at what am I looking at and how does it apply. Okay, the math by itself is not hard. None of these equations by themselves are very difficult, but it's the way we apply them that sometimes gives you guys a little bit of trouble. And that's it for now. Look for another video where I will go through some math examples and show you how we apply everything that we just learned.